My name is Steve O'Shaughnessy. I'm going to share with you some research that I've been doing as part of a PhD. I'm a BSides newbie, so it's great to be here. First one. It's also, because it's ongoing research, it's kind of a work in progress. So it's the first time I've actually spoken about this to anybody apart from myself and my wife and my supervisor. And I suppose as a researcher, no one really gives a rat's about your research, only yourself and maybe your supervisor when there's a deadline or something like that, but I digress. So, as I said, we'll get the introductions out of the way. This should work if I plug the USB in. So I'm currently lecturing in ITB, so I'm there around 3 years. 2 years full-time, and I was doing a part-time stint as well. I'm teaching mainly secure coding modules, so I'm teaching the students how to kind of put pen testers out of a job. Well, that's what I say anyway, but you know, it's never going to happen. Previously in the IT department, the Department of Education and Skills, I was there for about 11 years. Did all sorts of stuff. I did basic admin work, and then I moved into the IT department, did some web admin, and I was in the IT infrastructure department as well for a while. As I said, I'm also a PhD student, so this is what I'm going to be talking to you about today. And a shout out to the IRC, which is the Irish Research Council, and ITB, which are obviously co-funding this research. So, just some bird's eye view of the kind of methodology that I'm going through at the moment. I'm trying to triage methods of malware classification. So the method that I'm using is non-invasive, so I'm not using any kind of reverse engineering. So I'm in no way statically analysing or running the code in sandboxes or anything like that. Just to point out, it's not a substitute for regular analysis, malware analysis, and that's not what I'm trying to do. I'm trying to classify malware in terms of slotting in samples into their respective families, okay? Because there is some ambiguity out there. You probably see anyone that's used VirusTotal, there is a bit of ambiguity there in terms of the families that they actually classify each malware as. I'm using image processing and machine learning, so a quick overview. I'll go into this in a bit more detail. I'm basically converting malware binaries into grayscale images. This is a byte for pixel mapping, so the internal structure of the file remains intact. I'm using texture analysis then to extract features, and then I'm using machine learning then to create a model. So basically the model learns all of the different kind of patterns within the resultant images, and it gives you a model then that can hopefully classify unseen data. Then that's the whole point of it. Another thing as well, for those of you that are familiar with analysis, it's not static analysis really. Yes, agreed, it does take a byte for byte mapping to a pixelated image, and we are looking at the structure, but the whole thing is I'm taking out features of that image based on texture, okay? And the idea is with enough images and enough variants of malware that we can start to kind of recognize patterns in variants and hopefully recognize them as particular members of particular families. It's robust-ish against obfuscation. So again, this is a work in progress, so we've a bit of work to do, but the initial kind of results that I'm getting back are kind of promising. It's optimized well. That's what I'm doing at the moment. I'm working in Python, which is fairly slow in terms of some of the image processing. So I can use C bindings using things like Cython, which allow me to use the native C code, which is a little bit faster. So that's something I'm working on as well. I'm also looking at using OpenMPI, which is a parallel processing library as well, to kind of speed things up. Image analysis is very slow because you're going from, you know, you're testing and training images pixel by pixel, so it takes quite a long time. Sorry, pressing the wrong buttons. It's been a long day. Okay. So just a kind of an overview of malware, just fairly general. Continues to rise, so there's no newsflash there. Okay, so particularly in the last 10 years, it started to rise almost exponentially. If you look at the stats, I'll show you in a second. It's a very lucrative business. So obviously the financial motive is there to create malware, and we've seen a big upsurge. It's all over the news. There's lots of buzzwords and lots of ransomware stuff going on. Lots of talks today about ransomware, so we can see it's definitely something that's in the news. Very easily accessible, so I can get malware samples pretty easily from the web. Don't have to have any prior knowledge of anything. Just not have to know how to use the web. Little technical knowledge required. So if I download a sample and I want to create a variant, I don't have to have a lot of knowledge. I can download encryptors, cloakers, any type of obfuscator. I can download applications that will do it all for me. So I don't even have to tinker around with the code in order to change these around. And I can fire these variants out, and most of the time, if it's a good encryptor that you download or that you get a hold of, it'll pass by a lot of the antiviruses. So just some stats. These are from AV Test. If anyone is involved with malware in any way, you probably know what AV Test is. It's a German company that release stats. They're an AV testing company as well. They boast getting in around 600 to 900 million samples a year that pass through their systems. This first stat is for the total number of malware. So you can see from around 2007, the last 10 years, it's been rising almost exponentially. And we're currently at around 650 million as of 2017. So that's 650 million samples of total malware. So if we just contrast that for a minute with the actual numbers of new malware, you'll see that it's actually declining. So take from 2015, the two topmost bars on the histogram there, or the bar chart there, and you'll see that in 2015 it kind of peaked there at say 142 million. It dropped then significantly down to about 125 in 2016. So if you contrast that with the figures in 2016 for the total malware, which are around 600 million, you can kind of get an idea of the amount of variants that are floating around out there. Okay, so as I said, the problem with that amount of variants, there's a lot of ambiguity. You upload a sample to VirusTotal, you'll get maybe 30 or 40 hits, but you won't get every one of the AVs classifying as the same type of malware. Okay, so there's a lot of ambiguity there, and that's something that I'm going to try and look into and trying to solve with this system that I'm devising. The obligatory VT upload. So this is a VirusTotal upload of a Trojan called SetCrack, and you can see I got 38 positive hits from the antiviruses, and you can see that most of them there will identify it correctly as SetCrack. Okay, so they identify it correctly as that Trojan. So I passed it through a simple cryptor and uploaded it again. Okay, so the numbers dropped this time, so we have 11 positives. But the kind of interesting thing to note here is the generalization of the description or the classification of the malware. It's gone from what we saw on the last slide as being able to identify it as SetCrack down to something more generic. Okay, so some saying unsafe, high confidence that it's malicious, things like that. So the ambiguity is there with the classification of that. Okay, so the problem that I'm trying to solve with the method that I'm using is to kind of remove that ambiguity if possible. So if I fire in 300 samples of SetCrack, okay, I should say with reasonable or high confidence that they're all SetCrack, okay, not just to say that they're malicious. Just to give you an idea of what we're talking about. So when we transfer, initially I'm just dealing with portable executable files, so PE files. Initially, when they're passed in and they're passed in and they're transferred or mapped to the binary images. This is kind of examples of what we see. So because we're mapping bytes to pixels, we get a good representation of the file. So if you look here and here, these all equate to different various sections within the portable executable file. The headers, sections and all that are remained intact. So if we have obfuscated files, say for instance, we use encryption or encoding or some sort of cloaking, heuristic cloaking or something like that, generally we're going to get some sort of differences in those. But across the board, if we have just a variant that's changed in some way, maybe the code is reordered or some slight padding maybe put in, say maybe some null bytes padded at the end of it, you're not going to get very much difference in the actual the actual design or the actual texture of the resulting files. And that's kind of what my my kind of work is built on. Okay. It's nothing new as such. The kind of basis for this came from a guy called Greg Conti. Okay, so him and a bunch of other people did a couple of research papers around 2007, 2008 on reverse engineering binary files. So initially what he proposed in his work was an extension to the hex editor. So it was kind of the visualization of a hex editor. Come up with the notion of byte plots. So like the method I'm using, it's a byte for pixel transfer, called these byte plots. So he followed it up then in 2010 with similar, where he created a classification taxonomy. So his idea was to try and help researchers and investigators to give them a repository for analysis. Again, he did a bit more work on the actual structure of different binary files. So he looked at text files, binary portable executables, media files, and he also touched on encryption, packing and encoding. So we also noted back then that there were differences in the binary structure if the code was obfuscated in some way. The nearest work to mine was called Lakshmanan, I don't know whether I pronounced that right or not, Nataraj, who did use a similar kind of system for classification of malware. So he did the same method where he passed the the binaries into images, grayscale images. He used a global descriptor called GIST. Okay, so GIST is basically a whole bunch of filters. Okay, it's actually 32 different filters we call the Gabor filters. So these filters have different intensities and different orientations. So the idea is each time we pass the file through the filter, we pick up different orientations of the texture. So these are all averaged out and bunched together into a single kind of feature map, and that becomes basically the feature extraction of that particular file. And then that's used then to classify the file after that. He devised a data set of about 9,500 samples from 25 malware samples called the Mal-image dataset. So they varied from just straightforward code reordering. There was some had obfuscation in there as well. Most of them were just kind of slight variations of each other. Just some examples of the samples out of that data set. That's A dialer. So you can see the similarities between the variants there. That one is another example of something that's they're very, very similar. The next one then is, this one is an encrypted one. So you can see that there is differences in the textures. Okay, so there's a bit of code reordering there, and there's a bit of encryption there. So the entropy of the file equates to basically different textures, if you like. His findings were pretty good. He got around 98% classification accuracy. Some robustness with regard to obfuscation methods. So the ones that he did come across, he was able to identify within reason. He puts it down to pure encryption methods in a lot of them. He had one kind of interesting finding there, that packers generate similar byte images. So even though the difference between the original file and the packed file may be different, the the packed images produce similar, the packed files produce similar images, and so can be identified based on that specific pattern. Just some critiques on how I kind of base my research, or where I base my research from. Since it's based on global features, it's not robust against code section reorder and padding. So this filtering system uses an average over the whole file, if you like, so it's global features. So if you put a lot of padding in the end, say we add in a lot of null bytes or introduce a new section into the file, this starts to fall down a bit. Okay. A long model training time. So as I said, when you're dealing with image processing, there is the kind of bad thing about it is that it does have a long training time because of the fact that you're examining and processing pixel by pixel. This dataset was biased, so it didn't contain any benign samples. So there was no innocent samples in there. There's no, normal run-of-the-mill applications put in there. So just to give an overview of what I've developed so far, okay, as I said, this is a work in progress, so feel free later on to berate me or tell me where I'm going wrong and I can go back to the drawing board. So we have our malware samples that we're going to map into images, so we map them into grayscale images. These are passed through the feature descriptor, okay, which is a localized feature descriptor, which I'll speak about in a minute, called local binary patterns. These produce histograms for each feature, okay, for each set of features. So what we do is for all of the images, we concatenate these into a huge, it's basically a vector array, okay, but it can be plotted or visualized as a histogram, okay, but if we talk about it in terms of data, it's actually a feature vector array. These are concatenated and passed to our machine learning algorithm, which is the k-nearest neighbors algorithm that I'm using. That in turn creates a model. So when we have our model, we basically have all of the images trained, and we have them trained using this feature descriptor, okay, called local binary patterns. So the idea is once we have a model, then we can use that to pass in unseen data, data files, and hopefully classify them as into their respective families. So we can classify them either as obviously some sort of malware, or whether it's benign, whether it's innocent. So just take a closer look at the localized texture descriptor called a local binary pattern. So it's a text descriptor, so it's used for feature extraction of textures. It has been used and applied to different areas of computer vision as well, like facial recognition and DNA sequencing. But the beauty lies in its simplicity and how effective it actually is on classifying or extracting features from textures. So the actual way it works is pretty simple. It works by taking each pixel in the image and considering a neighborhood for each pixel. So the original one considered a 3 by 3 pixel neighborhood. Okay, this has been adapted and revised to also be taking a circular set of features as well, which is rotation invariant and scale invariant. Okay, but it doesn't really apply to us, and the calculation is pretty much the same. So the example I have there, we're looking to calculate the LBB code, the local binary pattern code for the pixel 4. So these numbers here are basically intensities of grayscale. So we know grayscale is 0 to 255. Okay, so from black to white. So anything in between has a basic number. So if we convert anything to grayscale, we have varying degrees of intensities, okay, from black to white. So these numbers represent pixel intensities, grayscale intensities. So the way the algorithm works, if any of the neighboring pixels have a value less than or equal to the center pixel, it's given a 0. It's thresholded, what we call thresholded to 0. Otherwise, if it's above, it's given a 1. So in the end, we get this binary number, which is converted back into a decimal, and that now is treated as the LBP code for that particular pixel. So this is repeated for every pixel in the entire image. If we have corners or sides, these are treated as zeros. Okay, so these are treated as zeros in the calculation, if they're corners or sides of the image. So the kind of resulting thing that we get, as I said, is a histogram, a feature vector of a vector of features that describe that particular image. So just to kind of illustrate the point, I took a picture of myself a couple of days ago. Well, no, that wasn't taken a couple of days ago. I took a picture from my folder a couple of days ago, and I passed it through the LBP feature descriptor, and it gives me this kind of hideous-looking picture. So it was kind of bugging me what that picture reminded me of over the last couple of days. So it hit me yesterday evening. I don't know whether it was just because it was a long day yesterday because I was finishing putting these slides together. I was tired. I was getting giddy, but I came up with this. So if anyone's old enough to remember who that is, Boris Karloff as Frankenstein. We used to love them all movies. But okay, so you might not kind of really see the resemblance there. I kind of did. So I ran Boris through the LBP again as well. So the image looks nothing like me through the LBP. But if you look at the histograms, they're almost identical. So it's kind of scary that I do actually look a bit like Boris Karloff and Frankenstein. Sorry, it was late when I came up with this, so it was just, I was getting giddy at that stage. So the learning algorithm that I use is k-nearest neighbours. It uses points within a specified neighbourhood. So I'll give you an example here. So this is our feature space. So these red dots and these green dots, they represent malware features, okay, a vector of malware features. And we're trying to classify what this blue star is. So we pick a neighbourhood. It's a case, it really is a case of when you're doing data analysis, it's a case of fiddling around with different size neighbourhoods and different weights and stuff like that. So for this one, we're going to take a figure of 3. So we're using k as the neighbourhood of 3. So if we take k as 3, we pick 3 nearest points to it. So that's done with Euclidean distance between the feature vectors. Don't ask me how to work it out on paper, but the classifier is pretty good at doing that. So we have, if we take the value of k is equal to 3, the 3 nearest neighbours to k are those 3 red dots there. So we can say with a kind of high amount of confidence that that blue star belongs to that particular family. Okay, so you can imagine if there's thousands and thousands of samples there, it gets quite complex. But that's kind of a simplistic view of how the actual thing works, and it's probably about as difficult as I want to talk about this evening. A big problem with data analysis is the accuracy of the model. Okay, so you can build a model, you can do training and testing and whatever else, but when you actually build a model and then test it against unseen data, it usually falls on its arse if it's what's called overfitted. Okay, so if we overfit a model, or sorry, if we overfit data, what we're doing is we're fitting the model too well to that data. So any kind of outliers or any kind of noise in the data at all, and if that picks that up as being, some sort of a relevant feature, then when you pass other data variants in, it's not going to recognize them because it's not generalized enough. What we're trying to do is generalize a model, okay, so it can pick up all variants. To try and combat that, it doesn't eradicate it, but it definitely does make it a little bit better, is a method called cross-validation. So what we do is take a training set, and we divide it into 10 or 20. It doesn't matter. You can divide them how many you want. I use 10. So one of the folds or one of the sections is kept as a test set, and the rest is trained down on the model and run against the test set. And it does this iterated through all of the different folds or all of the different sections of the training set. and then the result then is a average of each outcome. So it eliminates some of the kind of bias in terms of if the data set is unbalanced. So initially for benchmarking, I ran it against the mal-image dataset classifier, but I added in extra samples. I added in some benign samples, taken mainly from Windows 7 machines. So it brought the total up to around 20,000 or so. I used a few different metric scores as well. I used accuracy, so that's, everyone knows what accuracy is. The total number of positives out of the total data set. Precision then takes into account the total positives, are what we identified, over the total positives and total negatives. So it looks at the proportion of samples that, say, we predicted as a certain type of malware, and if it was indeed actually malware. Okay. The next one then is recall. So that takes into account the true negatives as well. Okay, or sorry, false negatives, and that's the kind of proportion of it's kind of proportion of samples from each class that were predicted correctly. Okay, and then the F1 score is kind of a weighted average between the two, precision and recall. Okay, so it gives a more kind of a smoothed effect. It takes into account the false positives and false negatives as well. So we can construct a confusion matrix. So anybody that kind of doesn't know what that is or hasn't seen before, it's just a simple matrix. So along the horizontal here, rows, we have the predictions, and then along the axis here we have the actual identifiers. Okay, so what they actually should have been. Okay, so we predict them as these, and these were what they actually should have been. So ideally we should get a diagonal all the way along here with yellow. Okay, so we're going from 0 to 1. Sorry, this is Matplotlib's default coloring, which is pretty bad. So the purple is 0, so it basically means I haven't classified any of the samples. And 1, it means I've got a 100% classification rate in those. So you can see all the yellow ones are all the desirable ones, the ones that we want. And the ones down here where we fell down a little bit with Obfuscator and Dial Platform, and then down here we have another couple as well. I think I've showed you a couple of examples there. So these are just two examples from these two classifications that were wrong. Okay, so we can see that there is some similarity in structure between them. I haven't done any kind of further investigation or any deeper kind of investigation as to why, because I'm not at that stage. We can only surmise that because they're fairly similar looking patterns or fairly similar looking textures, that may be why the classification model didn't find them or figured them out as something else. I got this guy Nataraj's code, and I ran the same data set, the extended data set through, and he's fared pretty well as well. He got a slightly lower score, but still pretty good, 97% over across the board. Just in terms of a comparison, time complexity, my method at the moment is 4 times slower, so roughly around 10 milliseconds for his sample per sample to actually process, as opposed to 40 milliseconds. I put that down to dealing with Python because, as I said, in order to process, we need to use what's called NumPy arrays. They're pretty slow when we're looping through those, so I'm looking to use the C bindings to be able to speed those up. I did, however, beat him on the actual training of the model. So it was roughly around 9 milliseconds per iteration. So that's per iteration of the classification of the training and test sets, as opposed to 48 milliseconds. So just to make things a bit more interesting, and exactly why the kind of basis why I'm basing this research, I decided to start obfuscating some of the samples. Now I couldn't use the mal-image dataset because all I could get hold of was the actual images. I don't have the original files. So I added in my own, another 5 different families. So I used various different types of techniques. Encryption using a FUD cryptor, byte cryptor. So I used basic encryption on that. I used a cloaker. I used a script from Mike Sumac. You can get it on GitHub. I actually used an updated version called PE Cloak. And then I wrote a script in Python just to add some bytes into the end of an executable. So all it does is extends the size of an executable, creates a header creates a section and updates the headers then and puts in a load of null bytes at the end. Okay, so it doesn't actually disrupt the running of the file. And the last one, I played around with some packers, so Empress, Petite, and UPX. I mean, there's stacks of packers out there, but I just picked, 3 arbitrary ones just to kind of see what the difference was in them. So all in all, I got an extra 4,500 samples. These are there. So CryptoWall, it's a fairly recent one. DryX is fairly recent. Shifu is fairly recent too. Trickster as well. ZMist I put in there because I'm an old fogey. ZMist is one of the old metamorphic viruses. It's gone since the late 90s, but there has been variants of it seen as near as 2012, so it's still in there. So I just threw it in there just for good measure. So this is just some examples of the samples that were when they passed through to images. So this is the encryptor that I use. So you can see that there's certain parts of this that it encrypted here. So it's kind of a bit more entropy. It's a bit more. There's a different texture there in the file, and that's basically the encrypted parts. But you can see that the more important parts, like the initial headers and some of the sections down here, remain the same. So there hasn't been any real change except for parts in the middle where there's some sections that were encrypted. The accuracy then, how it scored, it dropped down a little bit to 93%. Okay, so that's acceptable enough with an F score of 92. This is the new confusion matrix, which is really confusing because we've so much packed onto it. I had to shrink it down so you can actually fit everything in. So you can see that there is still a fair amount of 100% classifications, but it falls on its arse a bit here, and up here. So I'm going to just concentrate on just one section of it here, just to show you, to blow it up. So this CryptoWall padded one caused a bit of trouble for a few of the families here, of the predictions here. The CryptoWall padded itself had quite a high classification rate of 95, but others like SwizzerGen and Obfuscator obviously thought that they were CryptoWall. So I'll just show you the difference here. That's Swizzer, and that's what it was classified as. So there's no apparent kind of patterns that look the same there. And I'm not trying to say there is, but it obviously warrants a further investigation. It's not clear from the outset why this type of pattern was classified as this type of pattern, but obviously we'll have to do a little bit more digging. Just to go back there for a second again, if you look at the worst one there was this one here, the Trickster encrypted. So I decided to do a little bit of a comparison between myself and VirusTotal. So what I did was I wrote a script. This is partly due to why I was exhausted last night and giddy. I wrote a script for VirusTotal. So what I did was I uploaded all of the samples of Trickster, the encrypted ones. And then gleaned back all of the stat reports. So the stats there are basically all of the stats that the VirusTotal antiviruses found as Trickster. So for each of the variants that were uploaded, this is a score of what actually came back as Trickster. Okay, so it varies from 0 up to 30 was the highest, 30 out of 64. Antiviruses that actually identified as Trickster. Now, if you look at the actual scores, if you uploaded these to VirusTotal, they may be higher because I just picked out the ones that actually identified this as Trickster. So you can see the overall average score was only 16%. So I didn't actually fare too badly, sorry, in terms of my first kind of stab at classification. Just about what about unseen data. So this is the kind of stage that I'm at now where I've only started to build the models. I've only just recently finished building the models. And I'm starting to run them against unseen data. So I picked four samples just for this this particular talk and ran them through. So the stats there, roughly an average overall of 73%, which isn't too bad, but it falls down a bit on these two here. Quite surprising, because if you look at these two, they're quite similar. Okay, so these are Don Tovo and Fakerian, the two that did worst. Okay, so you can see that they're quite similar. Again, I haven't done enough research to find out why these are falling down and misclassifying these. Again, it's ongoing research. Just the limitations. So it has trouble with some samples, obviously. Okay, so it's fallen down in some samples. I haven't run them through the full data set yet. Cannot identify new malware. Okay, so if there's a new malware strain and it isn't trained for that to identify that particular malware, it won't actually find it. Okay, so it can only identify what it's trained to classify. Ambiguity with regard to classification names. So like I spoke about earlier with the VT reports, the virus total reports, there is a lot of ambiguity. Okay, yes, we may get a score of 38 out of 50 or 45 out of 60, but are they all classified as the same sample, as the same malware? And are they actually that sample that the majority say they are? Okay, so at the moment I'm working off virus total, and I'm using samples that are classifying these mostly as one type of family. Okay, but again, there is some ambiguity there that, I don't know whether we ever will get to a stage where we'll have a kind of a standardized way of classifying malware families. And it's slow at the moment, so I'm working on the build-up of that over time. Just for to do, sorry for anyone who's not from the Republic and doesn't recognise our old illustrious leader, just Google Bertie Ahern and Mahon Tribunal. That'll tell you pretty much all about him. So the next kind of phase, apart from, let me give my 3-minute warning on this. Apart from the increase in the data set and the ongoing testing, is to produce a hashed local hashing pattern. So when we went through the local binary patterns, we saw that thresholding was binary, so it was either given a value of 1 or 0, which is a very hard kind of threshold. Okay, so it doesn't take into account the kind of similarities between neighbouring pixels. So I'm looking into using some form of hashing, okay, some sort of a hashing scheme, to maybe kind of smooth over the differences between the textures. So if there's any kind of, say, code reordering or any kind of entropy, that it's a bit more kind of lenient in terms of being able to identify that pattern. I don't know, this is all just kind of in my head at the moment, so I don't know if this will actually work or not, but that's what I'm kind of working towards. As I said earlier, optimizing it with C bindings and open MPI. Looking into segmentation. So segmentation is a computer vision. It's a computer vision thing to basically segments the image into different regions, and then we can kind of identify each region. So for instance, I can break down a PE file into its different sections and then run the classifier over each of those. So if it's a case that most of the file stays intact, okay, I have a kind of a taxonomy or a kind of a repository of all those pieces. So I can use it just to identify those particular pieces. Because if it's only certain parts of the file that are encrypted or encoded, for the most part, judging by what I've come across, the encryption algorithms are fairly weak. Some of them are pretty strong. But the segmentation can and it will help to identify these a lot quicker. Add a lot more samples. obviously build it up and make the model better, stronger, more general to different types of families. And then tweak and test as much as possible so we can get the model as generalized as possible. So just to summarize what I've been talking about, I'm coming up with a new method for localized image features using machine learning. We're using local binary patterns, a texture analysis descriptor. It's not a substitute for dynamic or static analysis. I don't attempt to even go there. It's merely a classification model. More than just static analysis, so we're not just looking at the static structures of the file. We're actually breaking it down and looking at the common features of these variants. It's favourable results against the state of the art, which I've shown you there earlier on. Favourable results of what I've done against VirusTotal. That of course needs further work as well. And it's still a work in progress and still needs a lot of work. So that's pretty much it. That's all I wanted to say. Thanks for listening. I know there was a kind of an ominous talk going in next door. So, well, hence, that's why I've got a more kind of intimate setting here today. But yeah, if anyone wants to ask any questions or has any input, as I said, it's a work in progress, so I'm not really kind of, I'm really kind of, you know, finding my way with this at the moment. So if anyone has any kind of input, I'd be happy to take it on board. Too late in the day to ask questions, is it?
Is there any sort of maybe plans in the future to maybe look into deep neural networks and convolutional neural networks to let it discover the features?
Yeah, I was actually thinking that as a kind of an add-on, because as I said, it's part of the PhD. So I had looked at support vector machines, which were very cumbersome and didn't give great classification. But it's something that I definitely can look into. Yeah.
And then I suppose my second question was, I know you say you want to stay away from dynamic analysis.
Yeah.
But could the same techniques be applied instead of the bytes of the compiled binary processed them from Windows?
Yeah, absolutely. Yeah. That could be, yeah.
Like after a certain point,
yeah,
certain obfuscation techniques such as compression and encryption will already run the course.
Yeah, yeah.
So is there any way you could do that within like a VM to make it isolated and then take a process dump and run?
You can, yeah, you can. I've actually put that up as a proposal for a project for students this year. I don't know if anyone will take it on, but it was actually going around in my head that, yeah, if you combine it with even basic static analysis or even in a VM, run a dynamic and get some of the function calls and API calls and whatever else that you can get from it and transfer that to images.
But even a process dump instead of like the dynamic
yeah.
analysis looking at the function calls, like a byte for byte reproduction of the RAM.
Yeah.
So you use the same.
That would be actually interesting.
Conversion to image.
Yeah.
And use the same mechanism you've already built.
Yeah. There's a similar as well, I suppose, if you talk about the network too. I mean, if you take a PCAP dump, I'm sure that has, I haven't looked at it now, but I'm sure that has similarities in terms of you can maybe use a baseline and, you know, have that as, okay, this is my network on a normal day, and for any anomalies will show up as different textures in the file. I'm not sure, but I'm assuming that could be, yeah. So it could be applied to that, yeah. Absolutely, yeah. Is that okay?